Hello and welcome to Awesome Day 2024. My name is Peter and I have the pleasure of being your AWS technical trainer for this next session, Introduction to AWS Services, Networking and Security. In this module, I'll walk you through how networking works on AWS and discuss the various components that play a role. The AWS cloud is being used by millions of users. Resources are constantly being created even while we speak. When you think of deploying resources on AWS, you want to create your resources inside a virtual boundary that isolates your resources from other customers' resources. The service that can provide you with that is referred to as the Amazon Virtual Private Cloud, or VPC. VPC is a service that allows you to create your own private space within the AWS cloud. This is a logically isolated virtual network. You can use multiple VPCs to logically separate your workloads. For example, you could have separate VPCs for each environment, such as development, test, production environments, or it could be based on the different teams in your company. You might want to separate them out for security concerns because VPCs help you control the flow of your traffic. It's very common for companies to have hundreds of VPCs. Overall, VPCs allow you to control access to your workloads, whether that be public access to the internet or private access only to your on-premises or corporate environment. When deploying a VPC, we must allocate a range of IP addresses. VPC is a regional level service, hence it sits across multiple availability zones. We can then further partition the VPC into smaller networks called subnets. Subnets live in a particular availability zone. You can have multiple subnets in each AZ. These constructs allows us to create our resources inside these subnets across multiple AZs to ensure high availability. As you can see on this slide, we have two types of subnets, public and private. The public subnets can be accessed via the public internet. You might want to have a public-facing web application here, or maybe a Bastion or Jump host. We also have private subnets, which do not have direct public internet access. This means they are protected from bad actors on the internet trying to compromise your application. This lets you place your backend systems, such as databases or application servers, in the private subnet with no internet access. You can have multiple VPCs in the same region or different regions for that matter. However, you cannot have a single VPC spanning multiple regions. In this slide, we will talk about a few more features that sit inside a VPC. With the help of these features, we can achieve defense in depth. What this means is we have multiple layers of protection inside your VPC. With VPC, you can use multiple layers of security, including security groups, network access control lists, route tables, and the internet gateway to help control access to Amazon EC2 instances in each subnet. So firstly, we have the internet gateway, which acts as a doorway to connect the VPC to the outside world. This enables resources in your public subnets, such as EC2 instances, to connect to the internet if the resource has a public IP address. Then we have route tables. Route tables define how the traffic should flow. It contains a set of rules called routes that are used to determine where network traffic is routed to. For the public subnets, the route table must have a route that directs traffic from your EC2 instance to the internet gateway. Next, surrounding the subnets, we have network access control lists. These are virtual firewalls which act as a stateless packet filter and sit at the subnet level. It makes the decision of whether the traffic can enter or leave the subnet. If you want to restrict specific protocols or ports, or put in explicit block rules, then make use of these network ACLs. Next, wrapping around the Amazon EC2 instance, we have security groups. This is also a virtual firewall, which acts as a stateful packet filter and sits in the instance level. It makes the decision of whether the traffic can enter into the instance. By default, all traffic inbound is blocked, whilst all traffic outbound is allowed. Lastly, on your EC2 instance itself, you can install your own firewall and protection software. Now we are going to dive into a demo. This demo will show you how to deploy a photo sharing website using Amazon S3, DynamoDB, and Amazon EC2. This demo will give you a holistic view of architecting an end-to-end solution by integrating the different AWS services we have talked about earlier today. Let me walk you through the core architecture of this solution. First, our photo sharing website is deployed to a web server hosted on an EC2 instance. For this demo, I will act as the user who will upload an image through the website interface. The web application receives it and then creates a thumbnail of the image. It then uploads the image and the thumbnail to the S3 bucket and inserts its metadata into DynamoDB table. For the purpose of this demo, media content is limited to images. But the concepts covered here also apply to other types of media content. Let's now build our demo. The first task is to create an S3 bucket to store the media contents and configure its permissions. At the top of the AWS Management Console, in the search bar, search for S3 and choose S3. This takes us to the S3 dashboard. Choose Create Bucket and then configure. The bucket name, for example, an-my-bucket-2023. By default, content stored in Amazon S3 buckets cannot be accessed publicly. For our use case, we need to allow public access to the bucket, so users can download content. So under Block Public Access settings for this bucket, deselect Block All Public Access. Acknowledge the security warning by selecting I acknowledge that the current settings might result in this bucket and the objects within becoming public. Choose Create Bucket. While we want to allow downloads from the bucket, we don't want to allow users to list the contents of the bucket or delete any objects. Amazon S3 enables you to manage access to objects and buckets using bucket policies to configure permissions. We will now create a bucket policy to configure permissions for our S3 bucket. In the list of buckets, we choose the name link for the bucket we just created. Choose the Permissions tab. In the Bucket Policy section, choose Edit. I will now copy a policy document and paste it in the policy pane. And we click on Save Changes. We now have created an S3 bucket to store the media contents and configure its permissions. Next, we create the media database to store metadata information, such as title, comment, and publication date. Since we want our system to be scalable, we use Amazon DynamoDB to store the metadata information. At the top of the AWS Management Console, in the search bar, search for DynamoDB and choose DynamoDB. Choose Create Table. Then configure table name, for example, My Table. Partition key, EIB in lowercase. Choose Create Table. The table we created is listed under Tables and its status displays as Creating. Next task is to create our web server and deploy our photo sharing website to the web server. But before we launch our EC2 instance, we need to create a basic Amazon Virtual Private Cloud or VPC network. This VPC will be used to launch our EC2 instance. So, in the AWS Managed Console, search field, type VPC. Select VPC from the drop-down menu. We are going to create a VPC with a single public subnet. The web server is hosted in the public subnet so that it can reach the public internet. In the left navigation pane, choose your VPCs. Choose Create VPC and then configure Choose VPC Only. I'll give this a name, Awesome Day VPC. Allocate an IP version for CIDR block as 10.0.0.0/16. Choose Create VPC. Next, create a public subnet. In the left navigation menu, choose Subnets. Choose Create Subnet, and then configure the VPC ID, Awesome Day VPC. Give our public subnet a name, for example, public 1. For the availability zone, select the first AZ in the list. And for the IPv4 CIDR block, choose 10.0.0.1/24. And choose Create Subnet. Next, select the subnet we just created, namely public 1, and in the Actions menu, select Edit Subnet Settings. Select Enable Auto-Assign Public IPv4 Address. This provides a public IPv4 address for all instances launched into the selected subnet. Choose Save. Even though your subnet is labeled public 1, it is not yet a public subnet. A public subnet must have an internet gateway, which we will create in the next task. In the left navigation pane, choose Internet Gateways. Choose Create Internet Gateway and then configure for the name tag MyIGW, which stands for Internet Gateway. Choose Create Internet Gateway. In the Actions menu, select Attach to VPC. Then configure the available VPCs, namely Awesome VPC, and choose Attach Internet Gateway. This attaches the Internet Gateway to your VPC. So even though we created an Internet Gateway and attached it to your VPC, we still have to tell instances within our public subnet how to get to the Internet. So in the next task, we will create a route for Internet-bound traffic. For this, in the left navigation pane, choose Route Tables. We can see that there is currently one default route table associated with the VPC, called Awesome Day VPC. Within the Routes tab in the lower half of the page, notice that there is one route in your route table that routes traffic locally. It allows traffic within the 10.0.0.0/16 network to flow within the network, but it does not route traffic outside of the network. We will now add a new route to enable public traffic. So choose Edit Routes, choose Add Routes, and then configure the destination, which is 0.0.0.0/0, and the target. Select the Internet Gateway in the drop-down, and then select the displayed Internet Gateway ID that we just created. Choose Save Changes. Next, choose the Subnet Associations tab. Under the section Edit Subnet Associations, choose Edit Subnet Associations. Select Public 1 and choose Save Associations. The subnet is now public because it is connected to the internet via the Internet Gateway. In the next task, we will add a security group so that users can access your web server via HTTP. We discussed earlier that a security group acts as a firewall for your instance to control inbound and outbound traffic. In the left navigation pane, choose Security Groups. Choose Create Security Group and then give the security group name, for example, Web Server SG. As a description, set Allow HTTP traffic. For VPC, select our AWSome Day VPC. And under the inbound rules, choose Add Rule. Type will be HTTP. The source, Anywhere IPv4. And scroll to the bottom of the screen and choose Create Security Group. Security group is now successfully created. When we launch an EC2 instance in the next task, we will associate this security group to the EC2 instance. Now, from the AWS Management Console, use the AWS search bar to search for EC2. Select EC2 from the drop-down menu. And from the menu, select Instances and choose the Launch instance. From here, we will configure the launch details of my new instance. I'll give this a name, which will be My Photo Website. Next, select the Amazon Machine Image, or AMI, which provides the information required to launch an EC2 instance, such as the operating system. The Quick Start list contains the most commonly used AMIs. You can also create your own AMI or select an AMI from the AWS Marketplace, an online store where you can sell or buy software that runs on AWS. In this case, we will choose the latest version of Amazon Linux 2. Next, we will select the instance type. Since this is a simple web application, we will choose an instance type that is most appropriate for a typical web server. We will go with T2 Micro, which has one virtual CPU and 1 GB of memory. In the key pair login section, locate the key pair name drop-down menu, and we will choose Proceed without a key pair. Amazon EC2 uses public key cryptography to encrypt and decrypt login information. To log into your instance remotely, you must create a key pair, specify the name of the key pair when you launch the instance, and provide the private key when you connect to the instance. However, in this example, we will not be connecting remotely to the instance, so we do not require a key pair. In the Network Settings section, choose the Edit button and make the following selections. For VPC, choose the VPC with the name that contains AWSome Day VPC. For subnet, choose the subnet with the name that contains public subnet 1. In the Firewall Security Group section, choose Security Group Web Server Security Group, which we created earlier. Next, the Configure Storage section, we can leave the default choices alone. Amazon EC2 stores data on a network-attached virtual disk called Elastic Block Store. You will launch the Amazon EC2 instance using a default 8 gig disk volume. This will be your root volume, also known as the boot volume. Next, expand the Advanced Details section. Scroll down to the IAM instance profile and in the drop-down menu choose the Amazon SSM Managed Core role. This role is associated with IAM policies that grants any application running on the EC2 instance access to both S3 and DynamoDB. Scroll down to the Termination Protection drop-down menu and set it to Enable. This will prevent the instance from being accidentally terminated. Scroll all the way to the bottom until you see a field for user data. When you launch an instance, you can pass user data to the instance that can be used to perform common automated configuration tasks and even run scripts after the instance starts. Your instance is running Amazon Linux, so you will provide a shell script that will run when the instance starts. We will copy a pre-written script and paste it into the user data field. The script will initialize a Ruby on Rails environment on the EC2 instance, deploy the web application to the initialized environment, and activate the web server. Now choose Launch Instance. Choose View All Instances from the bottom of the page. The instance might appear in a pending state, which means it is being launched. It will then change to running, which indicates that the instance has started booting. When creating a new instance, there will usually be a short time before you can access the instance. Wait for your instance to display the instance state as running and the status check as 2 out of 2 checks passed. Now our EC2 instance has been successfully launched. Now we will test our deployment. We select a newly created instance and the Details tab displays detailed information about that instance. In the bottom pane of the console, under the Details tab, we can see information about the instance type, security settings, network settings, and more. We will now locate the public IPv4 IP address value and copy it to the clipboard. Let's open a new browser tab and then paste the public IPv4 address into the address bar and press Enter. Our photo sharing website is successfully launched. Let's now add an image to the application by choosing New and then providing the title, a description, some tags, and then add an image file. Let's jump across to the DynamoDB dashboard. In the left navigation pane, choose Tables. Choose Explore Items. Choose My Table. We can see the metadata of our media files, metadata as stored by the web application. We can also check how media files have been stored in the Amazon S3 bucket. Let's navigate to the S3 dashboard. Choose the name link of your bucket, an-my-bucket-2023. We can see the list of image files uploaded by the application in the bucket along with the thumbnail images. Congratulations, we have successfully deployed and tested our web application. In the above solution, we have seen how to deploy a photo sharing website using Amazon EC2, Amazon DynamoDB, and Amazon S3. In our demo, we deployed a single EC2 instance. Now, in the case of a single EC2 instance, you have a single point of failure because if the web application fails, the system is not accessible and cannot recover. And when there are a lot of requests coming in, the system might even become unavailable. To ensure high availability, you should deploy at least 2 EC2 instances across different availability zones. In a situation where you have multiple instances, the next problem you are going to deal with is traffic distribution. You need a load distribution method. To help with distributing your load evenly to the instances, you can make use of the Amazon Elastic Load Balancing Service, or ELB. Amazon ELB comes in multiple flavors. The application load balancer distributes traffic according to HTTP or HTTPS rules that you can configure, whereas the network load balancer uses TCP, UDP, or TLS-based rules. Elastic load balancers are highly available and can be used to decouple application tiers. This means your web tier doesn't need to be aware of the changes to the application tier infrastructure. It also supports health checks. The load balancer sends requests to instances sitting behind it. If the instance fails to respond, the load balancer will stop distributing traffic to that failed instance, resulting in a better experience for your customer. And then finally, we also get security features within the Elastic Load Balancer as well. We can use TLS termination on our Elastic Load Balancer to unburden your instances behind the scenes. For this demo, we will create a load balancer to see it in action. I have 2 EC2 instances here sitting in different AZs to ensure high availability. We are going to make the load balancer balance the loads between these 2 EC2 instances. So first select Load Balancer from the left. Click on Create Load Balancer. Select Create under Application Load Balancer. I will give my load balancer a name. And next, I will need to select the VPC in which my EC2 instances are available. Here I will select the AZs across which I need my load balancer to balance the load. Then I will select the security group for the load balancer. This security group allows HTTP traffic on port 80. Next, I need to set up the listeners. Listeners are going to check for traffic coming on the port that you specify here. In this case, it would be HTTP port 80. So I will leave it unchanged. I need to create a target group. Target group is where the load balancer will forward the traffic to. So my target group will consist of those 2 instances. I will choose instances here. Give my target group a name. Scroll all the way down and click Next. Here I will select both the instances that I want my load balancer to forward the traffic to. Finally, click Create Target Group. Let's go back to my page where I was creating my load balancer. Hit refresh here, and I will select the target group I just created. Scroll down and click Create Load Balancer. It will take some time for the load balancer to be created. Once it has been provisioned, scroll down to find the DNS name. Select the Copy button. And now let's open a new tab and paste the DNS name here. Here we go. We have one of our EC2 instances. Now, if I refresh this screen, it is redirecting me to the other EC2 instance now. So our load balancer is balancing the load between both of our EC2 instances. The Elastic Load Balancer is regionally scoped. It gives us the ability to distribute incoming traffic to multiple instances or applications in that region. But what if we want to distribute traffic across different regions? Amazon Route 53 gives us the capability to do that on a global scale. Amazon Route 53 is a DNS service that translates domain names to IP addresses. You can use it to register domain names and even perform automatic renewals or configure different routing options, which allows us to determine where traffic will go. It provides tools for flexible, high-performance, highly available architectures on AWS. So let's see how this works when put together. In this example, we might have a client or an end user that's trying to connect to our application that is sitting within our VPC. The end user would navigate to our URL. Route 53 would be used to resolve that into an IP address, which then leads us through our internet gateway to our Elastic Load Balancer, which distributes the incoming traffic to multiple EC2 instances, which then could respond back to the end user. And we're doing this all within our VPC within the AWS cloud. Next question to ask ourselves is, what options do we have for hybrid connectivity? That is, how to connect on-premise data centers to the AWS cloud. There are actually three ways to do this: OpenVPN connection, site-to-site VPN, and direct connect. To use OpenVPN Connect, our OpenVPN client will connect to an AWS client VPN endpoint. We also have our site-to-site VPN, which would require a customer gateway setup in the on-premise data center. And then on the VPC side, we need a virtual private gateway. This allows interactions between our on-prem data center and the cloud. We have one last option here. This is called Direct Connect. Direct Connect is a physical optical fiber cable that runs from your on-premises environment all the way to the AWS cloud. Advantage of using Direct Connect is traffic goes over a dedicated network link, which means no bandwidth constraints. You can choose the bandwidth yourself. With OpenVPN clients and our site-to-site VPN, traffic goes over the public internet, and you will be at the mercy of the speed of the general internet. In summary, Amazon VPC allows for the creation of logically isolated networks to launch applications. With VPC, you can use multiple layers of security, including security groups, network access control lists, and route tables to help control access to Amazon EC2 instances in each subnet. Finally, for hybrid networks, AWS offers different connectivity options such as site-to-site VPN, Direct Connect to connect on-premise data centers to the cloud. Next, we'll change gears and talk about security. Security is job zero at AWS. It is the highest priority. As an AWS customer, you'll benefit from a data center and network architecture that is built to meet the requirements of the most security-sensitive organizations. AWS infrastructure has been architected to be one of the most flexible and secure cloud computing environments available today. A key way to look at security on AWS, especially as a customer, is using this shared responsibility model. When you think about security in your on-premises environment, you need to manage everything, from physical security of the building to physical security of the IT devices, through to environment controls, operating system, application, data, etc. This results in a lot of administrative overhead without much benefit to your business. We previously heard the term undifferentiating heavy lifting, which referred to running the physical components of the data center. When deploying resources on AWS, we learned that AWS took care of this undifferentiating heavy lifting. That is, we manage all the physical stuff for you. This means AWS has some responsibilities when keeping the cloud secure. On the flip side, AWS does not have access to your data. We also don't have access to your resources. So there will be an element of responsibility that falls onto you as a customer. This is where the shared responsibility model comes in. It details and highlights what is AWS's responsibility and what is your responsibility. So let's take a look at two simple examples. Firstly, when using EC2, it is the responsibility of AWS to provide physically secure compute services that are available for your use. But when you deploy an EC2 instance, it is your responsibility to apply ongoing operating system patches. It is the responsibility of AWS to provide the ability to encrypt your EBS volumes. However, it is your responsibility to actually enable the encryption. We don't mandate how you must perform something. We provide you the options, levers, and controls. In a separate example, let's look at S3. It is the responsibility of AWS to provide a highly available and durable storage solution for you to use. It is also our responsibility to provide a permission structure that restricts public access. But it is your responsibility as a customer to determine what data resides in S3, whether it is encrypted or not, and who can and cannot have access to it. In short, AWS is responsible to provide a robust and secure cloud framework, a framework that provides you, the customer, the ability to operate safely and securely. It is your responsibility to make use of these options, to decide which data can reside where, and then to make informed decisions on how to deploy your services. Every service falls into the shared responsibility model. However, some services require more responsibility from you, the customer, whilst others require less. There are many services that can help you manage your security, from encryption to key management to web application firewalls and logging and monitoring, to name just a few. Let us now talk about how we can use AWS Identity and Access Management, or IAM, to authenticate users and control their access to AWS services and resources. AWS IAM gives you the ability to securely control access to your AWS resources. You can assign granular permissions to users, groups, and roles. You can share temporary access to your AWS account and also federate users in your corporate network or with an internet identity provider. When you set up your own AWS account, you require two things. You need, first of all, an email address. And you also need a password. Together, this will form an identity called the root user. Now, the root user is a powerful user. We call it sometimes also the super user of your account, and is the one that can do account level settings, like, for example, delete your account. For that reason, we typically do not recommend you to use the root user for day-to-day activities. On the contrary, one of the first tasks that our root user will do is to actually create an admin or administrator. Now, to use an administrator, to create an administrator, to give it permissions, we need a function called IAM, which stands for the Identity and Access Management Service. IAM actually does two things. First of all, it is used for the authentication. And second of all, it is used for the authorization. Authentication is all about the question, who? Who are you, and are you who you claim you are? So username, password is typically what we think about. The authorization is more about the what. What are you allowed to do? These are your permissions. So how do we define those permissions? Well, we'll do that through the use of a JSON style policy. And the way we remember easily what kind of fields we need to have into that JSON policy for each one of the statements, just remember about here. Because we need an effect. The effect will be either an allow or a deny. So are we allowing some permission or are we denying the permission? The action is basically the actual permission that we are using. And then finally, we have the resource upon which that action will be either allowed or denied. How can we do with this? We can attach this policy either to a IAM user, like for example our admin user that we're trying to create, a user group, which literally is a collection of users, which we generally recommend, because if you create for each individual user their permissions, you might have an inconsistent situation. By pre-creating a user group and attaching the permissions to the user group, we have a much more consistent configuration. And finally, also the role. Role is a really interesting one because the role represents temporary permissions. When someone assumes a role, they do not get all these permissions permanently, they get them on a temporary basis. Now, who can use those roles? The same users as before. In other words, our user has the choice either to have permanent permissions or temporary permissions. We can also use this for federated users. For example, a federated user would be defined by, let's say, Active Directory, which could be running in your on-prem, in your corporate data center, and that you would use as an identity provider to connect to IAM. And finally, the role is also very important for all our AWS services. An AWS service created in your account cannot talk to another AWS service in your same account if you don't give them the right permissions. And they will use a role for that. We previously talked about S3 for object storage. S3 is an example of a service that can have a resource-based policy attached. In this case, we call it a bucket policy. A resource-based policy is another type of IAM policy, but that is attached directly to the resource, such as an Amazon S3 bucket. And these policies grant permissions to the principal that is specified in the policy. Let's look at this example where you have created a new bucket. By default, only the owner gets access to the bucket. However, you might have content that you want to share to the public, for example, photos on your website. To do this, you can make the bucket public. But what if you want to just grant permission to specific users or services, or maybe a set of users, roles, or services? Controlled access can be granted with the help of those bucket policies, which can define who or what can access your bucket, from where and when. The bucket policies can be used along with identity policies we spoke about previously. Another way we can ensure the security of our data is to encrypt the objects in our bucket. There are various forms of encryption. S3 offers server-side encryption, so known as SSE, on objects by either using a customer-provided encryption key, a key managed through the Key Management Service, or KMS, or have S3 itself manage the encryption key. Using these forms of encryption enables S3 to encrypt your object when the data is at rest. S3 also supports the HTTPS protocol, which enables encryption in transit. AWS CloudTrail is used to track all the user activity that happens inside of your AWS account. Any API call made to your account, no matter whether it is through the console, CLI, or the SDK, Software Development Kit, all of these activities get recorded by CloudTrail. This can be very useful if you find something suspicious happening in your account. For example, who terminated my EC2 instance? Or who changed the security group settings, etc. We can also use this record in case we need to backtrack and understand how access was granted in the first place. The API calls are stored in a trail, essentially a log file. These trails can be exported to our S3 buckets, which we talked about earlier. By keeping all that information, we have the ability to answer common questions from a security standpoint about who made a request, what did they request, when did they make that request, and from where were they requesting. CloudTrail gives us the transparency in our account. Additionally, storing the CloudTrail logs into S3 allows us to reduce the cost of storing that important log data, and also grants us the ability to use various querying tools such as Amazon Athena, a serverless SQL querying tool. The last service I want to talk about in this session is the AWS Trusted Advisor. Trusted Advisor is a tool that sits in the background of your account and provides guidance on how to improve your account across various pillars: security, performance, fault tolerance, and cost optimization, along with identifying any service limits you're approaching or have hit. Trusted Advisor bases its guidance on the Well-Architected Framework, which is a series of best practices compiled by AWS to help build effective architectures. So how does Trusted Advisor work? Well, let's look at a cost optimization. Maybe you have a large EC2 instance, let's say an M5 4X large, for example, that has been operating at 10% utilization over the last month. Trusted Advisor may look at this and say, well, you can reduce the size of this instance and still meet performance objectives, and it will cost you less, so you can achieve some savings. On a separate note, maybe you have all of your EC2 instances in a single availability zone. If that availability zone were to have an issue, you could potentially lose your entire environment. So Trusted Advisor will give you a warning under the fault tolerance category, suggesting you deploy your resources across multiple availability zones. There are many checks that Trusted Advisor performs, which are regularly refreshed to give you updates as changes to your account and environment are made. Summarizing what we have learned in the security module. Security is a shared responsibility between AWS and the customer. Customers should carefully consider the services they choose because their responsibilities vary depending on the services used. AWS IAM enables us to implement a fine-grained access control to AWS services and resources. AWS CloudTrail is an AWS service that records API calls made by a user, role, or an AWS service. Finally, we learned that the AWS Trusted Advisor evaluates your account and provides recommendations that help you to optimize your AWS infrastructure, improve security and performance, and reduces costs. I hope you enjoyed this session and found it interesting. We would love to hear what you thought about this session. So please take a minute to complete the survey. Your feedback is important to us and can really help us shape and improve events and learning in the future. You can also reach out to us on the various social sites listed on this slide. And why not test your knowledge? Make sure you complete the knowledge check after this session to see how you're progressing. That's the end of this module. Next, join me for Module 4, Innovation with AWS. Thank you.